Hello and welcome to Lecture 19, Part 2 for Life in the Universe. In this video, we will conclude Unit H on the formation of planetary systems. And I guess our theme for this is something that it seems like over the last few decades, or at least couple of decades, we've come to realize more and more that a lot of the aspects of planetary system formation is rather violent. Maybe we were a relatively lucky system in terms of what happened in our early history. So, first off, it seems that kind of near the end of planet assembly, you're going to have a number of pretty big collisions. And some examples of that are, and I'm including Pluto here, even though it's no longer officially a planet. And let me come out of a share for a second so you can see it. For most of the planets, the um, rotation axis is reasonably close to perpendicular to the orbital plane. So let's say the orbital plane is horizontal across here, then the rotation axis might be something like this. I mean, ours is 23.5 degrees off being exactly perpendicular, which is too bad. For Uranus and Neptune, Uranus and Pluto, rather, Neptune's fine, but Uranus and Pluto, they're both tilted over something like this. They're almost in the plane of the orbit. And one plausible explanation for that is that they had some glancing collision with some fairly big objects, have to be quite big for Uranus, that would have um, basically reset the rotation. And if that is the case for Pluto, Pluto's moons would probably be debris from that collision. Speaking of moons coming from debris of collision, our moon is rather weird for a number of reasons. In general, its isotopic abundance of the various elements is a pretty good match to the Earth, indicating that we're in about the right place of the solar system for it formed. But the moon's core is quite small for something its size at this place in the solar system. Also, the moon is lacking in volatile elements. This would be elements that have relatively low vaporization temperatures. And our leading idea for how the moon formed is known as the giant impact hypothesis. The idea being that the early Earth formed without it and then was hit by an object about the size of Mars, something that would definitely call a planet if it had survived to the current day. In this somewhat off-center collision, the core of that impacting object ended up merging with the Earth and becoming part of the Earth's core. But some material from the mantle, in particular the mantle of the Earth, ended up in orbit around the Earth and condensed to form the moon. I will have a link in the description to a much better graphics thing from the BBC showing a simulation of this than the very low resolution simulation I've got in the little animated GIF here. It's from a larger BBC series, Do We Really Need the Moon? And I haven't watched the whole thing, so I don't know if we need the moon or not. If any of you haven't watched the whole show, let me know what the answer is. Mercury has kind of the opposite problem with the moon. Mercury has a very big core and a small rocky mantle for something its size in this part of the solar system. And there are a number of suggestions involving this. One possibility is that Mercury had a nearly head on collision with something about where it is now that completely removed a lot of the original mantle. As we're going to see in a little bit, planetary migrations where the orbits move around a lot seems to be a pretty big thing. It's possible that Mercury originally formed somewhere else in the solar system and largely through the effects of Jupiter's gravity had its orbit changed. It's possible that what Mercury collided with was Venus or the Earth. Now, if you look at the satellites of the Jovian planets, and they all have a lot of satellites, then you can kind of divide them into two categories, regular and irregular, based on the orbits. The regular satellites, which include all but one of the big satellites, the one oddball is Neptune's largest moon, Triton. But anyway, the regular ones are all the ones that orbit closer to the planet, in about the plane of the planet's equator, in the same direction as the planet's rotation, and in low eccentricity orbits. And here we probably had basically something kind of like the solar system in miniature, where the Jovian planets ended up with a circumplanetary disk as they were forming, and the regular moons formed from material that condensed and accreted in that circumplanetary disk. So this is a kind of a simulated view of Jupiter, showing the orbits of Io, Europa, um, Ganymede, and Callisto, the four big moons that Jupiter discovered. And then one of the inner moons is also indicated a little bit smaller. And then there are a few more smaller inner moons that aren't showing up here. But let's see, Amalthea is the one besides the one Galileo discovered shown here. But there are a few others, little ones in there. And so that would be the regular satellites there. Okay, let's zoom out. And here Jupiter is now that little dot right there that I just covered up with a little red dot from the PowerPoint pen. And this shows the orbits of many of Jupiter's irregular satellites. And you notice they're not very well confined to Jupiter's equatorial plane. Looks like a semi-random orientation. A lot of these orbits are a lot more eccentric as well as being further out. These are probably things that had formed further out, or not formed around Jupiter at all, but formed in this general neighborhood of the solar system, but were then captured by Jupiter's gravity. And one thing, if you look carefully, these aren't exactly random. Let's see how well I can trace some of these here. But you can see that they have kind of some clustering in the orbits. So it looks like you've got a number, say maybe clustering kind of right along here. There are definitely three or four of them that kind of here that all kind of seem to meet right in that area. So you tend to have among the irregular satellites these orbital families where you have multiple satellites for following similar orbits. And the thing is, to be gravitationally captured, you've got to dissipate some energy. And one way to do that is by being tidally fragmented. The term tidal force here refers to the difference in gravitational force from one side of an object to another due to some other object. And because it's the difference in gravitational force of the moon on the Earth from one side to the other, and to a lesser extent, the sun's gravity from one side of the other to the Earth, that cause the tides in the ocean. It's one of the effects, but that's why we would call in general that differential gravitational force is called the tidal force. And so, anyway, within these families, these are probably fragments of what was once one object, but likely through tidal disruption was broken up. That allowed some energy to be dissipated, and these fragments ended up then following similar orbits around Jupiter. And well, certainly Saturn, which also has lots and lots and lots of moons, you see these families of orbits among the irregular satellites. Now, it says something about orbital migration, so let's kind of get into that. And in the process, let's kind of try and figure out where the Oort cloud came from, because it's highly unlikely there would have been very much material that far from the protosun enough to form stuff from out there. So, one place the Oort cloud may have largely come from is that you think about what would have happened to what would now be the inner part of the Kuiper belt. So take the population of trans-Neptunian objects, but then the ones that would have formed closer to the sun, where the Jovian planets are actually orbiting now. And the thing is, if you're something little trying to orbit the sun in the neighborhood of something big, like a Jovian planet, that's not a safe place to orbit, because gravitational interactions will cause ultimately one of three things to happen to that little thing. It'll end up hitting one of the Jovian planets, in which case it becomes part of the Jovian planet. That'd be part of the formation process there. It could have the orbit modified where it hits the sun, and that's really the end of it. Or it could be ejected from the solar system and go out in interstellar space. And that's probably where Oumuamua and Borisov, which we talked about in the last lecture, came from. They were kicked out of some other planetary system and just happened to be, passing our way recently. Um, for However, you'd have some things that would be almost but not quite kicked out of the solar system, and that presumably is the Oort cloud. And so here we have a kind of an exaggerated view of how this happens. So starting right here, we've got one of these little icy planetesimals that's falling on a trajectory that's much more smoother than what I can draw here, and it has a close encounter with Neptune. And so you can have some orbital energy interchange between them, and depending on, it can go either way. But in this case, let's say that Neptune gains a little energy and the planetesimal loses some. So gaining some energy, Neptune moves a little further from the sun, a tiny amount, greatly exaggerated here. But the much less massive planetesimal is now on an orbit that brings it where it has to worry about Jupiter. And Jupiter, being the most massive of the Jovian planets, does most of the work here. So close encounter with Jupiter, again, some energy is exchanged. Jupiter moves a little closer to the sun, again, greatly exaggerated for a single encounter here, but our poor little planetesimal has been kicked out into the Oort cloud, if not out of the system altogether. Now, the individual effects on the um, on the Jovian planets for any one of these is minimal. But this is going to happen a lot. So the cumulative effect can be fairly large, and especially if Jupiter does most of the work. It's kind of a simple calculation to figure out, let's say that Jupiter kicks 1 trillion chunks of ice that are a kilometer in diameter out into the Oort cloud. So plausibly, there's that much stuff in the Oort cloud. So what would be the effect on Jupiter just from an energetics standpoint? And you'd find that to do that, Jupiter would have to have started about an AU further from the sun, at about 6 AUs, moving into about 5 when it did that. But that's not all there is to orbital migration, because you also have to look at interactions between the planet and the disk, the gaseous disk itself, especially when the distribution of matter gets to be non-uniform in the disk. So that can be quite complicated. And then it turns out the planets can even interact with each other when they're not that close to each other. And so right here, for an example, this shows something from simulation of interactions between Jupiter and Saturn. The time scale involved here. Sorry, it sometimes takes me a second to find the cursor for the pin here because it's very small. And my vision is far from perfect. So anyway, the whole length of time here is only 500,000 years, 500,000 years. So the bottom one isn't so important, but this shows the changes in the eccentricity of Jupiter and Saturn's orbits. And then the top here, though, shows the change in the semi-major axis of the orbit. The numbers for Jupiter's orbit on this side, and Jupiter is the black curve here, and the numbers for Saturn's orbit on this side, and Saturn's the gray curve. And you notice you kind of go through this period here where they're oscillating some and fairly rapidly, but no big changes. And then all of a sudden, you have this kind of up in, and then a really fast jump out, and then Jupiter jumps a few times and moves in a little bit. And in particular, in this little bit here, which occurs only over probably less than 10,000 years. Let's see how straight I can draw this line. Somewhat better than I've typically been doing. And then where we end up here, but in about less than 10,000 years, Saturn moves out more than an AU here, which is quite a huge jump there. So and and Jupiter doesn't jump as much, but it still jumps here. So these kind of scenarios are sometimes called jumping Jupiter scenarios. So when you look at all of this, This do all the various calculations, you find that mostly what this does is it moves Jupiter closer into the sun, moves the other Jovian planets further out. And this gives us a way to understand the hot Jupiter systems that we see around other stars. Uh, Except for, unless you can do it by the gravitational collapse of the gas, which we think usually doesn't work, we still think that probably most Jovian planets form by core accretion. To make a planet as big as a Jovian planet, you need to form them outside the snow line where you've got ice to build up enough mass fast enough. So probably what the hot Jupiters did is they formed further out from their stars outside the snow line. They just migrated inward a lot more than Jupiter did in our system. And we seem to have been kind of lucky in our system that our Jovian planets settled down in their orbits now are in a pretty stable resonance where they're not really interfering with each other very much. Some other exoplanet systems, it seems like this was much bigger things. You see significant larger eccentricities in the orbits, and including some significantly different inclinations even of orbits, even among big planets. And that didn't seem to happen in ours. Now, it's not clear if, on average, if that is going to be a good or a bad thing for terrestrial planets. If you have any terrestrial planets already formed when, say, Jupiter migrates past through this neighborhood on its way to being a 20th of an AU from the sun, then the orbits of those terrestrial planets get all screwed up. And if they don't hit the sun or hit the Earth or hit Jupiter or the Jovian planet migrating in as a consequence, they're kicked into orbits if they're even still bound to the system, such that they are not in good orbits for life. On the other hand, it seems that Jovian planets form and migrate faster than terrestrial planets do. So any terrestrial planets forming in the wake of such a Jovian migration, because the system would have been stirred up more, would might have access to more icy planetesimals hitting it and possibly more water. In fact, that's probably where a good bit of our water came from. As evidence that there was, in fact, a good bit of stirring up of things in the early solar system, we have the record of what we call the late heavy bombardment, and late only in terms of solar system formation, that we see in heavily cratered terrains among the terrestrial planets, such as the lunar highlands shown here. And you've had a lot of things hitting the surfaces of the terrestrial planets after their surfaces had already solidified. So it couldn't have been too early, but it largely shut down by about 4.1 billion years ago. And if the Jovian planets were doing a lot of migrating, but it settled down by the time this was over, sorry, 3.8 billion years ago was about when it ended, then as they did so, that would scatter a lot of the small solar system bodies around, and you would have expected, at least for a while, an increased rate of impacts on anything that's got a solid surface to still have a record of that. Now, last lecture, we also talked about this clustering of orbits and some trans-Neptunian objects. Sedna is one of them, so that's why sednoins is kind of used to refer to these. And we indicated this might be due to the presence of a fifth giant planet out beyond, good bit beyond Neptune. It turns out that models trying to start with some kind of early situation and see if you can get something that looks like the solar system we have now, they do a better job of giving the system we have now if we have a fifth giant planet in the system to begin with. It would be another ice giant, so planet like Uranus and Neptune, so mostly core rather than mostly atmosphere like Jupiter and Saturn. And anyway, if you initially had that somewhere between Saturn and Uranus, this thing ends up being ejected from at least the inner solar system by Jupiter and Saturn. In most of the models, it ends up being ejected from the solar system completely. So whether or not that is something that's encouraging for the idea of Planet 9 or not, but it's possible that Planet 9, if it's real, which that may be a big if, this maybe it started much further in, and the Jovian planets are somehow responsible for where it is. Although it's also the proposed orbits for where it would have to be now. It's far enough out where it's hard to see if Jupiter and Saturn could actually have gotten it into the orbit it's in now. All right. So this last little bit is just kind of summarizing the formation of the solar system timeline, starting the clock when the interstellar cloud begins to collapse, and at least getting up to 1,000-kilometer size pieces would call planetary embryos, and even getting the Jovian planets formed, and most of their migration takes place very rapidly. Because there's less material, terrestrial planets seem to form about factor 10 slower than the Jovian planets. The sun officially becomes a star after about 50 million years when hydrogen burning starts in its core. And from there, really up to about the next billion years or so, is what we might consider the cleanup, as the remaining gas and dust is swept out by the stellar wind, and you kind of finish up the end of the late heavy bombardment, kind of trickles down to a rate of collisions like we have today. All right, and of course, as we've said, the codes we're still doing for fun, but there'll be other questions in the attendance uh, quiz you need to go take on Plato. But I thought this is just kind of a good random thing here. This is one of the funniest things I think I've ever actually seen in a scientific paper about why they had some problems taking some of their data. So I thought wildlife versus astronomy is a good way to describe this. And I'm going to lead this slide faster than you're going to have time to read it. But if you want to read it, pause the video and you can do that. All right, I'll let you know when the lecture 20 videos are ready for you. Um, but anyway, probably best that you're keeping up with getting the attendance quizzes taken so they don't all pile up at once.